Hello and welcome everybody to the first video of Math Help Center. First and foremost, I do welcome everyone and anyone to subscribe to my channel for all things math and science related. My intention with this channel is to provide relevant lessons from various math courses, ranging from, say, the high school level, like algebra, uh, trigonometry, geometry, to more advanced mathematical courses, typically reserved for those students in either an AP course or even those starting, say, like the freshman year of high school, who maybe going into their first calc class or their first pre-calc class and aren't quite sure exactly, what exactly is going to be waiting for them. I also plan on providing videos related to physics in both at the high school level and at the college level. For those of us who are undergrads and are just looking for another sane voice to help explain those various concepts, as we all know, sometimes we want to hear it from another voice, another person, even though like we've been hearing it from our teacher, and it's just flying over our head. So sometimes it's helpful to just hear it from somebody else, hear it explained by somebody else. So I think that'll be very helpful for anybody that's currently or in the future would be watching. So for the first lesson of this channel is going to deal with an introduction to partial differential equations, as you could tell from the title. Now, why partial differential equations? Well, first of all, it's the only notebook I had on hand. However, I do want to start off with something, more importantly, I do want to start off with something that is more familiar to me, that I've completed this course recently, and it's still fresh in my mind. I still have that drive to finish this. So before we get started, once again, please, if anybody out there, which I'm assuming most of you are that are watching this channel, um, have any questions like with homework, or certain assignments, I'll be more than welcome to also take custom, say, like for example, custom recommendations for, say, a video that you want to have me explain a topic on, like for example, on linear algebra or whatever else it might be. So without any further ado, let's go ahead and get started. So what is a partial differential equation? Well, if you've recently taken an ordinary differential equation class, you know that an ODE, an ODE is typically an equation of one variable. And what I mean by that is that the function itself typically doesn't involve multiple variables, and even if it does, for example, say some function of, say, x and y, just for arbitrary coordinates, say we're only dealing with the x coordinate, and say the y coordinate is completely forgotten at that point. So first and foremost, PDEs, unlike ODEs, which again are ordinary differential equations, include more than one independent variable. So what's an example of this? Well, think back in your differential equation class, and when we were dealing with, say, a differential equation of one variable. The best example that I like to go back to is the Newton's law of cooling example. So if we remember from our ODE class, we remember that for this equation we have, it's typically represented with a capital T for the temperature and a lowercase t for the time. Now, for this equation, we know that the rate of change of the temperature according to the time, which is what the left hand of this equation says, so again, this is what the left hand of the equation has, is equal to some proportionality constant times the temperature, the initial temperature of, say, whatever you might have. And so in this case, you notice that our general solution will actually only be a function of time. It won't be a function of any other parameters such as, x, y, z, or whatever it might be, whatever other parameters you might be interested in. In this case, we're only dealing with one parameter. Again, this is the right-hand side. So, as opposed to something like this, a partial differential equation typically includes more than one variable. And the way we often annotate, or denote, excuse me, a partial derivative is with a curly u, with a curly d. I was looking at the u variable here. So again, in this case, we're saying a function of a function u, its derivative with respect to the x variable. Now we know this is a partial derivative because we see this curly d as opposed to the kind of like the more regular looking d that we have in our ordinary differential equation. So for something like this, we usually denote it in shorthand because sometimes writing partial u over partial t can get a little bit cumbersome, especially when you're dealing with really big equations. So a lot of times as mathematicians, we like to reduce these down into a more easy to read form, if you will. So typically we often denote this as u sub, or whatever the variable is that we're trying to take derivative of. So in this case, our function is u, but the derivative that we're taking the respect to is x. So we want to know the rate of change of the function u with respect to the x variable. That's essentially what this equation here is saying. And again, we can denote that using shorthand notation. And again, you could do this for, say, partial u over partial y. That would be equal to u y. Again, with the subscript is often denoted as the variable in which we want to find that, in which we're taking the derivative in respect to whatever function that we're dealing with. Second derivatives, on the other hand, are a little bit trickier in the sense that maybe the notation is a little bit more, it's just a little bit more, but it's the same idea. So for example, say I had a second partial derivative of the function u with respect to, partial x and partial y. So again, we know that this is just equal to, again, our function is u, and you see that the first derivative we have is respect to x, and the second derivative is respect to y. So in this case, we're just going to write it subscript x and subscript y. Again, these are denoting the same thing. So if you ever see these, say you see the right-hand side of these equations in a math textbook, or whatever it might be, your homework, just know that they're denoting the same idea. In general, however, a PDE can be written as, and this is going to be a little rather chunky function, but let's see if we can get it all in one line. So that's xy, and then uy, xy, however many variables you're going to need. And typically we often set this equal to 0. Now that we know this, and again, this is important because typically this is how PDEs are set up. It is also very important, rather I would say it's very imperative, that's how much I want to stress this, is our classification of partial differential equations. So if you remember back to ODEs, when we talked about classification, we often talked about it in terms of the number of derivatives that we often had to apply to a certain function. So what I mean by this is that typically classifications of the said PDEs are dealt with by the variable quantity. So again, that's the first That's the first important note. The second one is that it's also done by the order of highest derivative. Again, the highest derivative. For example, say I'm given, and I'll just write the example, just so we know that the following is an example. Say we have a function of u, uh, say u sub x plus u sub y is equal to 0. So as you can see, an equation like this, since we're only dealing with that first derivative here, we would say that this equation here is it's a first order partial differential equation. Likewise, say I had another function, the same function u, but this time we take, say, two derivatives of the y function equals 0. So again, because this one denotes at least two partial derivatives, and because the requirements require us to go by the order of the highest derivative, the highest derivative here is of order 2. Again, because we're dealing with two derivatives of one single function. So this would be considered as you can probably guess, if the first one was considered first order, this would be considered a second order PDE. Essentially, we say that it goes to the nth degree for the nth number of derivatives. Okay? And let's go ahead and see if I can go to the next page. Oh, there we go. Third of all, and I think this is also very important, is that we often like to classify and write PDEs as using a linear operator L. So what does that mean? Well, and again, say we have a function, let's say uxx minus ut equals 0. And again, if we write this in our differential form, this will essentially just be the same thing as partial squared u over partial x squared minus partial u over partial t is equal to 0. Again, these are the exact same. These are equal. Now, if L, so again, if assuming our linear operator L if our linear operator is defined as L, is capital L, then the linear operator in this case, say for example this equation here, the one with the partial notation, we would say that our linear operator is just going to be equal to partial squared over partial x squared minus partial over partial t. Now notice how the linear operator looks very similar to our equation up here, except it has one thing missing, and that's the variable u. As you can see, we don't have this variable in our linear operator that we do in our full equation. So why is that case? Well, the importance of the linear operator has to deal with the fact that often when we have a differential equation, we can have multiple solutions to a set equation, given some parameters for example, like boundary conditions or initial conditions, whatever it might be. The purpose of the linear operator is to help us to visualize, or rather help us to conceive, The notion that if, say for example, we have two solutions to a differential equation, then linearity would imply that the sum of both of those two original solutions can be combined, and that would make for a third solution. So again, it's the idea that we can linearly combine solutions to form new solutions that are still just as valid as the original solutions that we originally found. So in this case, since our function was u, remember, our function was u, that would imply that if we apply this linear operator to the function u, the way we would define it as the linear operator of the function u is again equal to partial squared u over partial x squared minus partial u over partial t, and again all that equal to 0. Likewise, we can, we don't have to use u. We can use basically any variable as long as, again, it matches, whatever that we're dealing with. So for another example, we can say use the variable v. In this case, it'll be the exact same thing, except we replace the u in our differential equation with v. So again, this would be something akin to partial squared v over partial x squared minus partial v over partial t, and again, that just equaling 0. So let's just define some terms in terms of our linearity. So in definition, and this is important, because it's defining something. It's defining our linear operator. We would say that L is linear if we would say L is linear if, and we have two requirements, L of, say, some function u plus the linear of some function v is equal to L u plus v. And also, L of some constant c, it can be anything, just as long as it's some constant, our function multiplied by some constant is equal to that constant multiplied on the outside times our linear operation of u. So again, these two definitions are very important when considering linearity for a function. If a function does satisfy both of these requirements, then it is said to be linear. Finally, let's consider the following equation. And this might be kind of big, so I wouldn't recommend memorizing this. It's more so for a it's a guide to allow you to verify how our differential equation is defined as. So in general, we're going to let's consider the following. Let's consider some differential equation with constants of a sub, say nm of the function uxx plus 2a 1 2 uxy plus a 2 2 uyy plus a1 u sub x plus a sub 2 u sub y plus a naught u, and all of this equal to 0. And again, I'm going to just put this in a box just because it's a framework for allowing us to decide whether a function is, a differential equation is being identified as a certain way. And again, I'm just going to denote here that a sub nm are all real numbers. So in this case, they're just constants. So from this, we're going to define another theorem. And again, you don't have to memorize this, or you don't have to copy this precisely. The big idea is just more so how we can apply this theorem to the equation above. So if we recall from our linear operations, our theorem is going to be using a linear operation transformation here we go, of the individual variables the PDE can be reduced to one of the following cases. So depending on a couple of factors, we can either define the PDE as parabolic, hyperbolic, of course, the last one, ecliptic. Or excuse me, elliptic. Now, I'll get into the importance of why it's important to be able to identify PDE in terms of whether it's parabolic or hyperbolic or ecliptic in a later video. For now, just know that in terms of, say, like an equation like the one we have above in the box, using various formulas, we can figure out exactly what kind of partial derivative, excuse me, a differential equation that we have with us today. All right? All right, so I think that'll be the end of the first video. Like I said, it's getting pretty long. But again, we're gonna stop here because later on I want to go into some more examples, specifically some examples of real world PDEs that we can essentially derive from from our real world, and show essentially what our understanding is as so far in a more tangible and less abstract way. Um, so again, just for now, I want you guys to just absorb this, go over it. And if you'd like, I can also post these notes up so you can have access to them at any time. If you want that, just go ahead and comment down below to let me know. And again, if you guys have any other suggestions for any of the other kinds of videos, just send them to me. I'll link my email, hopefully, in the description. And for that, I hope you guys have a great day.